All right, now we're really going to hit what we want to get to in 10.2, and that is this area problem. That is finding the area under a curve. And so there's going to be a lot of different slides here, as you'll see in your PDF notes, but we'll go through quite a few of them pretty quickly because just a little bit on each slide. Now, first of all, what this problem is asking us to do is it's asking us to approximate the area under the curve of negative x squared plus 10, that's the graph that you see here, on the interval 0 to 3. So that means that we start right here, and that we're going to end right here. So we're not going to do the whole piece of that curve, but we're going to find all the area under here, get as close to the actual area as we possibly can. So that's where we're going. I'll show you how we use these rectangles of the area problem in calculus to accomplish that. First thing is we try 3 rectangles, for instance. It doesn't have to be this, but it can be. This is a good place to start. It shows us that we can, we're going to put these rectangles in there, and we're going to get it so that it touches the edge of this function at each spot. Now, if you'll notice this, you look at these rectangles and you say, that doesn't look like it estimates it very well, because we've got a lot of empty space that's not being filled in, and that's not being taken into account by those rectangles. And you'd be right by thinking that this is just not a very good approximation. So what we do in order to make a better approximation is we make those rectangles thinner, and we make more of them. So you'll notice here there are twice as many, they're twice as thin, and as you can probably tell, the amount of wasted space is much less. It looks like we're getting closer to the actual value. I'll show you some real values here, some of the numbers in just a little bit. But still, not the greatest estimate, so we get twice as thin, twice as many rectangles. As you see now, there's even less wasted space, and it just keeps going that way. So the idea here, like I've mentioned before in the previous example, is as the number of rectangles increases, the area gets closer and closer to the actual area under the curve. So that's the idea, is that we just keep getting more and more and more of these. Now, if we didn't have computers to help us with this, or if we didn't have calculus to help us with this, it would be a really tedious task. But the approximation gets better as n, that is, the number of rectangles, approaches infinity. So we want to get just an infinite number of these little tiny rectangles in this problem. Now what we'll do is I'll go through and actually show you some numbers so you can get an idea of how close we are. So there is an actual real value for the area under that curve. We'll get to that at the end, but here's our first estimate. When we break it up into 3 rectangles, it's not very good, but as you can see here, I'm just finding the area of each rectangle. This big one was 9, this little one was 6, and the smallest one was 1, and we add those together, we get an area of 16 under that curve. Again, not the greatest estimate to this, as we can see. But then I break it up a little bit further, and the area of these rectangles, as you might notice, we have to get a little bit nastier numbers. The width of each rectangle now is 0.5. We're not taking up an entire unit, and in this case the tallest one goes up to 9.75. That's just where the rectangle intersects the curve on each one of these. And so you'll notice that it touches on the right hand side of the box in each case here, and that's where we're getting these numbers inside the parentheses. You'll see I've taken all those area formulas, I've added them all up, we get 18.625, so that area is a little larger than what we had for the last one. That's kind of what we expected. We continue to do that, and what we find is, well, that we get a little bit better estimate. We have a bunch more rectangles. As you can see, the calculations are getting more tedious. The width on each rectangle is 0.25. The height, again, is going to be just where we touch the function on the right-hand side of each one of those. And so it's going to get closer and closer to the actual value, and that's what we're hoping for. Now, the when we add all of these up, what you might be able to see down here is that it's 19.84375. Okay, so that's getting better. It's getting closer to our actual value of 21. Now, how do I know that actual value? Well, that's where the calculus comes in. That's a question that I'm not going to answer for you in this lesson. That's something you'll have to find out along the way when you are taking calculus. But there is a way to do it. We will learn about that at some point. For now, though, just know that as you get more and more rectangles, the approximation gets better and better.